Hello, everyone. So this is me from the future, I guess from when you started watching these videos. It sounded like there are some audio issues like last time, so now I am here with shorter hair, re-recording kind of what we talked about in these videos. So in the last video, we kind of did a big recap of all of the things we saw last time in terms of disjoint sets, the implementations of those through kind of going through quick find, quick union, weighted quick union. And then now in this video, we're going to do something a bit different. And it's going to be a very kind of different approach to how to make our structure more efficient. So we're going to use this thing called path compression. Now, before I explain what path compression is, I want to explain kind of a high level takeaway for like what we're going to try to accomplish here. So far, everything we've done has always been about preserving invariance. So we've always had some invariant in our structure, and we wanted to make sure that if we ensured that invariant, then we would hopefully have efficiency, like something like the AVL invariant. Now, what we're going to do here is a bit different, where since we have a little bit less structure, we're going to do a little bit of extra work in our data structure so that future calls to the same operation will be faster. The idea is to, instead of trying to get efficiency for this operation, while we're doing our work, if we just do a little bit of extra work, maybe an analogy being like cleaning the campground kind of while you're there, then it would be better the next time you're there. And so the idea is you might have a slow operation at first, but future ones might be more efficient. So here's the big idea. The idea is, since we have to kind of climb up this tree going up when we're going through find in this weighted quick union structure, we could go ahead and just compress that path. Now, remember that the exact structure of the tree doesn't actually matter to the state of the disjoint sets. All we really care about is that all of the things that belong in one set kind of point to the same root. And so the idea is, if we're already having to do the work of in finding 15, starting at the bottom and going all the way up to the top, then if it's not too much extra work, we could go ahead and just change all of the pointers of all the nodes we visited. Oh, that meant to go forward. We could just change all the pointers to point directly to the overall root of all of the nodes we visited. Since we have to visit them anyway, if we just do a little bit of extra work, some constant amount of work on top of what we're already doing, then hopefully future calls to find would be more efficient. And the idea being that just changing this pointer should be cheap. We already have to do all of this traversal up this chain in the first place. And so we're only adding an extra constant amount of work onto what we were already doing. But then in future calls to find of 15, it will now be fast because we can now immediately go to the top. That's the big idea of path compression. Anytime we do find, all of the nodes that we visit along the way up, we change to point to the overall route. And that's just an additional constant factor of work on top of the looping we were already doing to kind of go up the tree. And so that is only a small amount of inefficiency added, but now on future calls to find, for the same value, should be constant time. So one other thing that's a bit weird when trying to talk about the runtime of these operations that kind of improve themselves over time is it's not really clear like how to apply our case analysis or algorithmic analysis on it. So we're going to run this path compression anytime you call find, even if it's a find inside a union. Remember, when in union, you have to find the roots. We'll compress then. Now, we're going to have to introduce a new term of kind of what is the average runtime over many different runs. We call this amortized analysis, where you're trying to talk about the runtime over a sequence of calls rather than just a single call. The term amortized doesn't come from CS in particular. It's a common term. Sometimes you think about amortization in terms of like payments. So like my car insurance, I pay once every 6 months, and it's a huge bill every 6 months. But for the other 5 months, it's free. I'm not paying anything. And you can think about, instead of just that one-time cost, you can think about being amortized over that 6-month period. The same idea is here. You might have one find operation that's really expensive, but all the future ones will be really, really fast. And it's just giving a word what we've been describing this whole time is kind of like our in practice case. Like when we're talking about hashing or arrays, and we said, in practice, resizing won't be that efficient. The idea being is, yes, that one call where resize happens is totally inefficient. But then we get a bunch of calls for really cheap. And that kind of averages out in a sense that on average, the whole thing will be kind of a cheap operation. Now, we're not going to talk too much about the details of amortized analysis. I'm going to hand wave this a bit, so we're not giving this a formal definition like we did with algorithmic analysis. But I do want you to know at least that term comes up a lot when we talk about this in practice case, having a few expensive operations compared to many, many cheap ones. So now that we kind of have that, let's try to talk a little bit about what this runtime is. So when we talk about amortized analysis, we normally talk about, well, what's the runtime over something like M distinct calls? So for example, if we had this weighted quick union without path compression, and we called find M times, well, then the runtime here would be something like theta M log N. The reason is we have a log N operation, that worst case weighted quick union find, you have to go up a tree of height log N, and we're doing it M times. So we have this like M log N runtime. And it turns out that with find on weighted quick union with path compression, it has this other runtime that we call M log star N. Log star is what we call the iterated logarithm. I'll explain what that means in a second. But first thing I want to remind you of is when you're talking about simple log, like when you have something like log base 2 of n, what that's saying is how many times can you divide n by 2 before you get a number that's 1 or less than 1. The log star, the iterated logarithm, is very similar in some sense, but slightly different. Log star of n is the number of times you can apply a logarithm to a number before getting something less than 1. So instead of dividing by 2 each time, you log the number each time, and you keep doing this until you get something like 1. Now, one thing in the next slide, I will show you kind of some specific numbers that make this a little bit clearer of kind of give you a sense of what this thing looks like. But basically, this log star is something that's going to be faster than log n. I'm not going to have you focus on the details of how to derive that this fact came from log star. That's a bit complex. But what I do want us to talk about is kind of getting a sense of the scale of what this log star is. So when we're talking about this iterated logarithm, it's going to end up being very, very, very fast. Now, what I mean by that is when we're talking about this log star, for all reasonable input sizes, it's going to basically be constant time. So here I have a table of n and what the value of that log star is. So when n is 1, the iterated log of n is 0. When n is 2, the value is 1. 4 goes to 2. 16 goes to 3. In order to get the value of that to go to 4, you have to increase the number to 65,536. And then to increase that to 5, you need to give it an input of 2 to the 655,536. That is a astronomically large number. Astronomically probably isn't even the right word. That is a stupidly large number. If you're curious for reference, there are about 2 to the 256 atoms in the whole universe. That is so many more elements. So there is no way you will actually have a data structure with this much stuff. You would probably need all of the computers in all of the world combined to get anywhere not even close to that. So for any sized input, really, this log star is going to be less than 5. So this is essentially constant time. Now, it's not technically constant time, partially because it's an amortized runtime. It's not a worst case runtime. In the worst case, we still have that log of n, that first time you're calling find on something. But all these future ones are going to be cheap. And the way that the math technically works out, it spits out this log star thing. But importantly, that log star is essentially constant. So no matter how much data you have, it's going to be basically constant time, or in all reasonable assumptions, less than 5 steps. So to kind of recap everything we've just seen, we kind of talked about kind of this journey starting from our baseline, which was mapping kind of like set IDs to all the elements in that set to quick find, to quick union, to weighted quick union, and now we have this path compression. And we started with this thing that had really bad runtime. Every operation was O of n, which was just not great. And then we kind of got something with this weighted quick union with path compression. We got it down to basically constant time for every operation in the disjoint set. This find, the union, the make set, all of those things, even though we have those log stars, they're totally basically constant time, assuming n is some reasonable input size that would fit on a computer. So this is just such an incredible feat of data structure engineering. Every operation is basically constant. When we started, kind of that not being clear we'd be able to get there from the start. Now, I do want to mention that there's a caveat here of another star, but a little bit different than the iterated log star, which is this is talking about amortized runtime. So this kind of in practice case. We still have a logarithmic runtime in the worst case, particularly that first time you call find. That first time you call find, you're going to have this worst case logarithmic runtime. But on the future calls, it's going to be fast. And so this kind of log star is a more mathematically precise way of capturing that. But importantly to mention is that that's only true and like average in practice. So to kind of, give you kind of one last recap, showing you a slide that we kind of talked about last time, here's to kind of give you that visual picture of kind of what all this stuff does, kind of where each point along the way, we kind of introduced a new technique and how that improved our runtime. So you might find this to be really helpful when thinking about how to contextualize all the implementations we've talked about so far. Now, in the last video after this, we're going to talk a little bit more about Kruskal's in particular, how now that we have this disjoint set, we can analyze the runtime of Kruskal's, and talk about one last optimization we want you to make when it comes to implementing this on Project 4.